Hey class, welcome back to chapter 22, Analyzing and Interpreting Graphs. Today we'll be looking at relations of the form y equals kx to the power of n for n equals or n values of 1, 2, 3, -1 and -2. Okay, so we have discussed only straight line or linear graphs so far in this module. Straight line or linear graphs for the sake of today's exercise in order to be consistent with the remaining non-linear graphs that we're going to look at. They have the form y equals kx, where n is 1. So x has a power of 1, we have a linear graph. For the sake of this exercise, there will not be a y-intercept. The graphs will only pass through the origin. Okay, so we're looking at graphs that look a little bit like, that's my axis, we're looking at that, or we're looking at that. It looks a little bit like a compass, okay? But we're looking at those kinds of graphs, okay, where they only pass through the origin. New to probably your knowledge, okay, are parabolas. So this is the first time they've been introduced in the module, okay? Parabolas have the form y equals kx squared, where n equals 2. And k is just a multiplier, okay? So if we looked at a linear graph, k would be what we normally call m. It's just our gradient, okay? So for an x squared graph or a parabola, parabolas are symmetrical around the y-axis. So if I have my x and y-axes, okay, x and y, okay, I'm looking at a graph that looks like this, okay, and my y-axis, this is not very well drawn, okay, but we can see that the line sort of mirrors across the y-axis. This point here, where we stop going downwards and start pointing upwards, that's called our turning point, or TP for short. For the sake of this course, all turning points will occur at the origin. When k is less than 0, we have the parabola occurring below the x-axis. So what that looks like, okay, if I have my x and y, again, okay, and if I flip my graph, I get a graph that looks like that, okay? So still the turning point is at the origin, okay? But instead my graph is below the x-axis and flipped upside down. So here we have a happy face for k is greater than 0, and if k is less than 0, we have a sad face, okay? And finally, k is just what we refer to as the dilation factor. So when we look at a linear graph, a higher value of the gradient, or m, or in this case k, will stretch the graph more upwards. A smaller value will stretch it downwards. So what that looks like in comparison, okay, if I have I'll just draw two positive graphs, okay, x and y. Okay, if we have this here being our normal just y equals x squared graph, okay, if I was to increase the value of k and draw this graph, okay, y in this case might be 2x squared. Sorry, it's very small to write in, okay? So the turning point hasn't changed, but the graph has now sort of pulled upwards, okay? Similarly, if I wanted to flatten out the graph, I'm looking at this kind of graph, this might be y equals 1/2 x squared. So when I'm talking about a k value of less than 1, we're talking about a fraction or a decimal for k, okay? Sorry, that was not drawn very well, okay? So that's sort of the difference if we just have our normal y equals x squared graph where k equals 1, higher values of k will stretch the graph or sort of squash it in towards the y-axis, and lower values, so fractional values, will flatten it out. And that's the basics of a parabola, okay? Let's look at cubics next. So cubics have the form y equals kx cubed, okay, so x cubed, cubic, where in this case the power of x, or n, is 3. K is still referred to as the dilation factor, and if we have k is less than 0, then we flip it in the x-axis. So I should probably start with what a cubic graph looks like. Okay, so that's my x-axis and that's my y-axis. My cubic graph looks a little bit like, I'm drawing very low to the bottom, this. Okay, so that might be my y equals kx cubed graph. If I have a value of k is less than 0, all that does is it again flips the graph. So x and y on my axes. This time my graph is going to go this way. So this top part has moved down to the bottom. And that's for, sorry, k is greater than 0, and this is k is less than 0. Okay. This sort of portion of my graph has flipped downwards and the other half has flipped upwards, okay? So it's a reflection in the x-axis. We also still, in whatever cases, have a turning point at x equals 0. So the turning point, again, is when the graph sort of stops becoming, how do we describe this in a way that sort of fits what we've covered so far? So in this case, as we're moving across in the x values, okay, we've become positive, 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 and then we become less positive, and then sort of increase it again, okay? Here again, we sort of hit that point where it starts to flatten out, and then it starts sort of curving back out again. All right, same as with the x squared graphs, okay, higher values of k are going to squish to this graph much closer to the y-axis, and larger, so it's kind of going to look like that, and lower values of k, so again, fractions are going to squish it a lot closer to the x-axis. All right, moving on to our negative powers of x this time. So hyperbolas have the form y equals k over x, which can also be written as y equals kx to the power of -1. Okay, and so we have that power of -1. This might take you back to our index laws in year 9. Okay, so these graphs approach both the x and the y axes, but they will never touch them. Okay, so again, we're not looking at any sort of movement in this course. Okay, if I have my x and y axes, again, these graphs look a little bit like this. So they approach both x and y axes in the quadrants, but they never touch them. Okay, so what that means is that we call the x and the y axes asymptotes. Okay, so asymptotes, the graph never actually touches it. It will approach those lines, but never physically cross over them. Okay. K is still the dilation factor, with large factors of k pulling the graph away from the axes. Okay, so larger values of k, if this was my graph of y equals k over x, or 1 over x, I should write, sorry, 1 over x, okay, then a larger value of k is going to pull the graph this way, okay, so that might be y equals maybe 2 over x, okay, and to flatten it out or to bring it much closer to the y-axis again, okay, we're kind of looking at that green line, okay, that might be a y equals, it could be 1 over 2x, okay, so that has a k value of 1/2 again, all right. So that is the basics. If again we wanted to flip the graph, we would make k negative, and then we would have graphs in the opposite quadrants, okay. Finally, the last type of nonlinear graph that we'll be looking at in this course is called a truncus. So these have the form y equals kx squared, or over x squared, where n equals -2. So we can also write that as y equals kx to the power of -2. Okay, these graphs look a little bit like this. So if I have my x and y axes, I have this shape. So similar to the hyperbola, but both are positive now. Okay, so it kind of looks like the trunk of a tree. Okay, if you think back to how you used to draw trees in primary school, we're looking at that sort of shape. Primary school, maybe you still draw trees like that. I still draw trees like that. Okay, again, they are similar to hyperbolas, but the y-axis is a line of symmetry, so we can flip it across the y-axis. All right, same thing, our k value as it changes can bring the graph closer to the line, okay, by making it a fraction. So that might be the graph of y equals 1 over 2x squared. Or we could stretch it further out. So we could have a graph that goes a little bit higher up and sort of like a wider, okay, and that might be y equals 2 over x squared. Okay, so similar sort of function across all of these nonlinear graphs. Your k value will do the same thing. It will mirror the graph as well if you need it to in the negative axis. We're not dealing with any, for my method students, we are not dealing with any transformations. We're not moving the graph across the x-axis. We're not moving it up and down on the y-axis. These cases are the only cases that we will be looking at within this course. In the next exercise, we will be discussing how to convert these back to linear graphs, just as we did in our statistics module. But for today, we just need to recognize the features of these graphs and be able to sort of plot them, which we can still do on our CAS calculator just by entering in those powers or writing it as a fraction. Okay, so when in doubt, use your CAS to see what kind of graph you have. That concludes today's lesson, guys. As always, good luck with the work, and if you have any questions, send them through, but otherwise, take care, and I'll speak to you all very soon.